Hello everyone. Welcome back to this lecture series on structural mechanics. In today's lecture, we move from trusses to another very important structural element called the columns. Columns are vertical compression members which are used in buildings, bridges, towers, or even the industrial structures. While beams fail mainly due to bending, columns fail primarily due to buckling instability. Today we'll study Euler's theory of columns, which explains the behavior of long, slender columns under axial load. Let us begin with the basic idea. When a short column is subjected to axial compression, it fails due to crushing of material. But when a long, slender column is subjected to compression, it does not fail by crushing. Instead, it suddenly bends sideways and collapses. This phenomenon is called buckling. Euler's theory explains the elastic buckling behavior. Here, the failure occurs not because the material reaches its crushing strength, but because the column becomes laterally unstable. This critical load at which the buckling occurs is called the Euler's critical load. Now, Euler's theory is based on several important assumptions. These assumptions must be clearly understood. Number one is column is initially perfectly straight and it has a uniform cross section. The material is homogeneous and isotropic. It obeys Hooke's laws. Here the stresses are within the elastic limit and the load is perfectly axial and concentric. As always, sulfide is neglected and the failure occurs by buckling alone. In practice, no column is perfectly straight, but these assumptions helps us develop a theoretical model. Now coming on to the sign conventions for the bending moments, when a column bends, if bending produces convexity towards the original axis, it is taken as positive. On the other hand, if the bending occurs concavity, it is taken as negative. This sign convention helps while forming the differential equation. Let us now derive the governing equations. When a column is subjected to an axial compressive load, Euler's formula is used to calculate the critical load for a column or a strut, and it has been given as Euler's load is pi square EI by LE square, where E is the Young's modulus or the modulus of elasticity, I is the least moment of inertia of the section of the column, and LE represents the equivalent length of the column or the strut. Now we shall go with the first condition, that is when both the ends of the column are hinged. So if that is the case, you can see the bending will be taking place in this way and you will have the slope will be developed at both the ends of the column. Since both the ends are bent or hinged, slope has been developed at both the ends, whereas the deflection is arrested at both the ends. Now the bending moment at a section which has been taken here, at this section the bending moment has been calculated as at this point, which is P into the perpendicular distance is Y. Okay, P into Y. And this will give a negative bending moment. So as we know that M can be calculated as, in general, it will be EI into d square Y by dx square. That is the second derivative of the deflection. So equating that one, that is M is equal to EI into d square Y by dx square, which will be equal to P into the horizontal distance is Y. And it is a negative 1. So simplifying this one, I am just bringing that Py within the left side. You will be getting EA into d square Y by dx square plus Py is equal to 0. And secondly, I am bringing that EA or dividing the entire equation with the EA, you will be getting d square Y by dx square plus Py divided by EA is equal to 0. This is a fundamental differential equation of the column buckling. So now the solution of this differential equation is y is equal to c1 cos x into root under P by EI plus C2 sine x into root under P by EI, where C1 and C2 are the constants which has been developed because of the integration. Now, we need to find this C1 and C2. And this solution, after finding the value of C1 and C2, this equation or this solution gives the buckled shape of the column. So for which we need to find C1 and C2. So how to find out this C1 and C2 is, we are going to apply the boundary conditions. That is what I told. Here at this point, we have the deflection is equal to 0, as well as at this point also the deflection is equal to 0. That is the condition we are going to apply. That is at the point B, y is equal to 0. That is deflection is equal to 0. That is here only the reference axis has been taken. Therefore, at x is equal to 0, y is equal to 0. So when we are substituting this condition, that is x is equal to 0 and y is equal to 0 in this equation, left side this one will become 0. Coming on to the right side, this is 0 and this is also 0. So the entire component will become 0. Now cos 0 will be 1. So in that case, this entire component will be equal to C1. Whereas sin 0 is 0. Therefore, this entire component will become 0. Therefore, what you will be getting is C1 is equal to 0. So the first constant has been found out, that is 0. Next, I need to find the C2 value. So for finding the C2 value, I am going with the second boundary condition, that is at this point also the deflection is 0. That is at the point A. So also at point A, y is equal to 0. That is now the distance of x from the point B is L. So at x is equal to L, y is equal to 0. Now already we found the value of C1, that is 0. So the remaining equation what you will be getting is this one, that is y is equal to C2 sine x into root over P by EI. That's it. Because already we found C1 is equal to 0, this entire component will become 0. So this is the one that we are having, and we are treating at x is equal to L, y is equal to 0. So substituting, left side will be getting 0, right side you will be getting C2 sine L into root over P by EA. That's what has been written here. Okay, so now we have that is sine L into root over P by EA, which will be equal to 0. But now we can see that the C2 will be there, right? Again, I'll go back to the same thing. We have this one, 0 is equal to C2 into sine L into root over P by EA. So this C2 should be equal to 0, or sine of this component should be equal to 0. But C2 can't be 0 because already C1 has been taken as 0. Once if C2 is also been taken as 0 in the sense, this column will not bend or buckling will not be taking place in this case. So that is the reason C2 will not be equal to 0. Rather, this component will be equal to 0. That is sine of L into root over P by EA is equal to 0. That's what has been given here. Right. So sine of something is equal to 0. So that you will be getting that theta is equal to either 0 or pi or 2 pi or 3 pi. In terms of pi's, you will be getting. So now taking the first practical case, that is L into root over P by EA is equal to 0. We can take that one. So next initial component will be taking that is equal to pi. That is L into root over P by EA is equal to pi alone, we can take it. Now squaring on both the sides, you will be getting this one as L squared, and this root will be getting cancelled. On the other side, you will be getting pi square. So L square P by EA is equal to pi square. So we need the P only. That is what is the Euler's load. So P will be equal to pi square. EA will be taken to the other side, numerator pi square EA divided by L square. So this is what is the condition for finding the crippling load. Once if the column is having both the ends being pinned. And now we can see that here under the pinned condition at both the ends will be getting the lowest critical load among all the 4 cases. Which means that a hinged column is free to rotate at both the ends. Therefore, it is more prone to buckling. Next, let me go with the second case wherein one end is fixed and the other end is free. That is, the point B is fixed and the point A is free. So once if the force has been applied along the axis, since there is no restraint at the point A, it tends to sway in this direction. Whereas this point will not sway because it's a fixed end. So now this sway distance has been taken as delta, over which only the column has been sway at the point A. Now again applying the bending moment at that section here at a distance x from your reference axis. This is what has been reference axis for all the cases. At a distance x, I need to find the moment about this point, means you'll be having p into this distance, that is this particular distance to be taken. This distance has to be taken, whereas we know this entire distance is delta and this distance is y. Therefore, moment will be equal to p into delta minus y. And again, it is going away from the axis. Therefore, you'll be getting this one is a positive value. So, m is equal to ei is into d square y by dx square, which will be equal to p into delta minus y. So now rearranging this one, that is multiplying within the bracket, will be getting p delta minus py. And that will be taken to the left side also. Py will be taken left side because we have a variable y, and on the right side both are constant. So we can take it outside itself. So now again dividing the entire equation with the ei. So we'll be getting d square y by dx square plus py by ei is equal to p delta by ei. Now, this is again a differential equation. So, the solution for this differential equation remains same with a small variation that delta alone is an exceptional one in this case. Therefore, y is equal to c1 cos x root over p by ea plus c2 sin x into root over p by ea. This is constant that we have got in the previous case also, plus this remaining term which is the delta. Now, this c1 and c2 are the constants of integration. Those two things has to be found out by means of the boundary condition. That is, in this case, the boundary condition is at this point deflection is equal to 0. That is, at B, y is equal to 0. As well as at the same point B, we have dy by dx, that is slope is also equal to 0 because it's a fixed end. Right. So those two only we are going to apply. That is, at the point B, we are going to apply the first boundary condition, y is equal to 0. That is, this is the reference axis. Therefore, at x is equal to 0, y is equal to 0. So, substituting this one, left side will become 0. Right side, x is 0 in the sense, this entire component will become 0. Therefore, cos of 0 will be getting 1. This entire component will be 0. Whereas, coming on to this side, this entire component, the bracket within that one will become 0. So, sin 0 will become 0. Therefore, this component will be nullified. And remaining thing is delta. So what you will be getting is left side 0, right side c1 plus delta. Therefore, c1 will be equal to minus delta. So we got the value of c1. Next, I need to find the c2. Now, the entire equation is available. Previous case, we got c1 is equal to 0. For finding the second, for applying the second boundary condition, we eliminated this one because c1 was 0. But in this case, we have c1 is available. So the entire equation has to be taken into account for the second boundary condition. That is the slope at any section to be found. So slope in the sense, this is the deflection equation. So slope has to be found. That is dy by dx. So the first derivative, now you can see that we have cos is there. So differentiation of cos, you'll be getting sine. And we have the variable is available. So that has to be brought outside. So what you'll be getting is here minus c1 into the bracket, whatever which is available, the x should not be taken because that's a variable. So that is why, again, I'll show it here. So the differentiation, I can write it here. So dy by dx, which will be equal to, keep the c1 as such, c1, and then whatever which is available in the bracket, that has to be taken outside, that is root over p by ei. And cos of anything differentiation will get minus sign, that is minus sine x root over p by ei. So this is the first component. Going on with the second component, plus again c2, keep it as such. Here the bracket within the square root has to be brought it outside into p root over p by a, and sine of anything, the differentiation will become cos. So cos x root over p by e. Right? So this is what the equation you'll be getting, and delta will not be coming because it's a constant. Differentiation of the constant will be 0 itself. So we got the second condition, and already we calculated delta is equal to what is that one? Minus delta. Sorry, C1 is equal to minus delta. Therefore, this entire component will become delta. Now, we are going to apply the second boundary condition, that is at B is equal to, at B dy by dx is equal to 0. That is slope is equal to 0. So, substituting in this one, that is at x is equal to 0. Right, at x is equal to 0, dy by dx is equal to 0. So, substituting this one, left side will become 0. Coming on to the right side, we have dy by dx, that is x is equal to 0. So, this entire component will become 0 and sign of this component also will become 0. So, the entire component will become 0. Now, going on with this case, we have this could have been put it in a bracket also. So, this bracket will become 0. Cos of 0 will become 1. Therefore, you will be getting 0 left side. Right side, you will have only this component is available. That is C2 into root over P by E. Now, anything, either C2 is equal to 0 or root over P by E is equal to 0. And whatever which is available within the bracket is a constant that won't be 0. Therefore, C2 is equal to 0. Right. So, now at point A, right, at point A, we have the deflection. The deflection is delta. That is what this way. So, that is nothing like at x is equal to L over the distance of L, y is equal to delta. So, we can apply this third boundary condition also in order to solve for the unknowns. Right. So, now applying that one, we'll have delta will be equal to C1. This is C1. C1 has been already calculated minus delta. So, minus delta cos L into root over P by EA. Why L came is, it was x. So, at x is equal to L. That's why this x becomes L. Plus delta alone, because C2 has been brought into 0. So, the second component will not come. So, plus delta, or otherwise, you can see this delta and this delta will be getting cancelled. Therefore, you will be getting 0 is equal to minus delta cos whatever which is available in the bracket. And this delta can also be equated to 0 because it's a product only. So, this also can be treated as 0. Therefore, you will be getting cos of L root over P by EA will be equal to 0. Right, that is nothing like cos of theta which will be equal to 0. So, applying the conditions, will have L into root over P by EA will be equal to pi by 2, that is cos 90, right, pi by 2 or 3 pi by 2 or 5 pi by 2, in which odd numbers you will be getting, that will be equal to 0. And again, we are going with the first practical case, that is first one pi by 2, we will be having L into root over P by EA will be equal to pi by 2. And again, squaring on both the sides, we'll be getting this is L square and P by EI. On the left side, we'll be getting pi square divided by 4. Squaring on both the sides. That's what you'll be getting. We need P only. So, P will be equal to pi square EI. And the denominator, we have 4 only. And the L square will be brought downwards. So, pi square EI by 4 L square. So, this is regarding the second case, when the column one end is fixer and the other end is free. Then the third condition is one end is fixer and the other end is pinned or hinged. Right. So, in this case, you can see at the point B, deflection is 0 as well as slope is also 0. Whereas with respect to point A, deflection is equal to 0, whereas theta is not equal to 0 because we have the slope. So, that is what the boundary condition we are going to take it. And again, now we are going to find the moment about the section about this point, which is being taken at a distance of x from the reference axis P, point B. So, it will be P into Y. Okay, P into Y. Right. So, that will be a negative one. And again, we can see that one more force is also acting. That is the horizontal reaction, because it's a Pindian. So, Pindian in the sense, we will have the horizontal reaction also will be that. So, that will be h into total distance is L minus x. So, this is distance is nothing like L minus x. So, that is what has been written here. So, m will be equal to EA into d square y by dx square, which will be equal to the moment due to this P will be minus Py, and the moment due to this H will be H into L minus x. Okay, and we can bring this Py to the left side as well as this Hx also to be brought to the left side. Right, so or else we can keep it as such. We'll bring that Py on the left side. And again, the solution for the above differential equation will be similar to the previous case also. And again, you can see that this P alone will be brought to the new denominator. So that is what has been there as a constant. So remains other terms remains the same. That is y is equal to C1 cos x root over P by EA plus C2 sine x root over P by EA plus this one H by P into L minus X. Now again, we can apply these three boundary conditions, that is at x is equal to 0, that is here at x is equal to 0, y is equal to 0 as well as theta is equal to 0, and here at x is equal to L, y is equal to 0. These are the three boundary conditions we are having to solve for this unknowns. As usual, C1 and C2 are the constants of integration. Now we are deriving for the slope also, because we are going to apply this condition also, that is at x is equal to 0, theta is equal to 0. So differentiating this, what is that one? The deflection equation, will get dy by dx, which will be equal to, since this is within the bracket, we can bring it outside, that is C1 root over P by EA, and cos of something, differentiation will become sine. So minus sine x root over P by EA. This is for the first case. For second half, we'll have plus C2, again within the square root, we can bring it outside, root over P by EA into sine of something, the differentiation will become cos. So cos x root over P by EA. And this term will come only for the x component. Other terms will not be coming. Right. So that's what has been written here. You can see that H by P alone will be there. So here H by P, I can write it separately. This one can be elaborated as H by P into L minus H by P into X. Whereas this one is a constant, differentiation will not come 0. Whereas this one, differentiating this one with respect to X, will have only minus H by P. That's what has been written here. Okay. So now we know that at X is equal to 0, we have that dy by dx is equal to 0. That is slope is equal to 0. That's what has been taken. At point B, y is equal to 0 as well as theta is also equal to 0. Let me start with the y is equal to 0. That is at x is equal to 0, y deflection is equal to 0. So substituting this one, going on with the previous equation again, I'll go back to the previous slide. So this is what is the deflection equation. Once if I am applying x is equal to 0, y is equal to 0, left side will get 0, right side, this component will become 0. Therefore, this C1 alone will be available. Whereas this component will become 0 in the sense the entire component will become 0. And going on with this one, we can apply x is equal to 0 means we'll have h by p alone will be there. Right. So in that case, we'll have 0 will be equal to C1 plus h by p. Therefore, C1 will be equal to minus h by p. That's what has been written here. C1 is equal to minus h by p into L will be there. Sorry, that has been missed out. So h by p into L. Right. Now applying the second boundary condition, that is at x is equal to 0, dy by dx is equal to 0. That is slope is equal to 0. So substituting here in this case, we'll have the left side is 0. Coming on to the right side, we have x is equal to 0 in the sense this term will become 0. The entire term will become 0 because sine of 0 will become 0. So the entire term will become 0. Coming on to the second half, this component will become 0 in the sense the total will be getting as C2 into root over P by EA because cos of 0 will become 1. And remaining thing is we have minus h by p. Okay, so that's what has been written here. 0 will be equal to C2 into root over P by EA minus h by p. Or otherwise I need P C2 only. So taking this one h by p to the other side, you'll be having h by p into root over the inverse because we are taking to the other side. So in that case, root over EI by p. Right. So now one more condition is at A, that is at this point, we have slope is available. Therefore, y alone is 0 at this point. That is at x is equal to L, y is equal to 0. So substituting that condition also, we'll have this equation like this. Okay, 0 is equal to minus h by p into L into cos, whatever within the bracket plus h by p into root over EA by p into sine of L root over p by EA. Okay, so that is, if you are bringing on the other side, we can see this will become h by p. I'll write it here, h by p L cos L into root over p by EI, this root, which will be equal to h by p root over EI by EI by p into sine L by L into root over p by EI. Now you can see that both the sides h by p is available, so we can eliminate those two. Right. So the remaining terms we can see that left side we have what is that from cos is that right side we have L sine is there. So coming both the sides taken together in the sense, we'll be having this one. Let me have this one as same. We can have only these terms which will be coming onto the right side. You'll be getting tan of L into root over P by EI will be equal to the remaining term, that is L into root over P by EI. Since it has been taken to the other side, this P will be going to the numerator and EI will come to the denominator. Right. This is nothing like tan theta which will be equal to theta. That is the case. Whatever which is available within the bracket is equal to this one. That's why tan theta is equal to 0. So in this case, we have whatever which is available within the theta will be equal to 4.5 radians. Once if we are having a numerical calculation, whatever which is available in the bracket which will be equal to 4.5 radians. Right. So now we can see that it has been written in this way, L root over P by EA which will be equal to 4.5 radians. So taking square on both the sides, we'll have L square P by EI which will be equal to 4.5 square. That's what has been written here. And this 4.5 square which will be equal to 20.25. Right. So now we have P is equal to 20.25, bringing this EI on the right side, and L square to the denominator will be having P is equal to 20.25 EI by L square. So if I want to write this one in terms of pi in the sense, this will be equal to approximately 2 pi square, 20.25 which will be equal to 2 pi square. So solving this one, you may be getting near to the 20.25. So removing this 20.25, we can write this equation as P is equal to 2 pi square EI by L square. So this is the governing equation for finding the crippling load when one end of the column is fixed and the other end is pinned. Next, the final case is if both the ends are fixed. This is what is the real-time case in most of the interior columns, wherein both the ends are both at the top as well as at the bottom will be fixed. So at that case, that is here in this case, at x is equal to 0, we will have y is equal to 0 as well as dy by dx is equal to 0. Similarly, at this point also, at x is equal to L, we will have y is equal to 0 as well as dy by dx. That is, slope is also equal to 0. First, we shall start with writing the governing equation, that is the bending moment at a given section about this point. We can see that we'll be having the end moment is also there. Since it is a fixed end moment will be there, that is m naught. So m naught minus p into the horizontal distance y. And taking this variable to the left side, we will be having EA into d square y by dx square plus py which will be equal to m naught. And bringing this EA, that is dividing the entire equation with the PI, you'll be getting d square y by dx square plus p by EA into y which will be equal to m naught by EA. Right. So the solution for this differential equation, again similar to the previous one, now we can see that again this p has been brought to the denominator on the right side. So y will be equal to c1 cos x root over p by EA plus c2 sin x root over p by EA plus m naught by t. So this is the condition for finding the deflection if both ends of the columns are fixed. Now C1 and C2 are the constants due to the integration, and we are going to apply the boundary conditions. Before which we can find the slope also, because we know that at this both the ends slope is equal to 0. So in order to find the unknowns, let me have the slope equation also. Again, this has been already written, that is dy by dx which will be equal to slope. This one, this is C1 into root over P by EI into cos of something will become sine. So minus sine x root over P by EI, put it in the bracket, plus C2, bring it whatever which is available in the square root over P by EI into sine of something will become cos. So cos x root over P by EI. Right. So this term will not come because it's a constant. So this is what the equation will be getting for the slope. That's what has been written here. Now we can apply the boundary condition. That is at x is equal to 0. We have 4 boundary conditions are there. At x is equal to 0, we have y is equal to 0. And again at x is equal to 0, we have dy by dx is equal to 0. Similarly, at x is equal to L, y is equal to 0, and at x is equal to L, dy by dx is equal to 0. So these are the 4 boundary conditions that are available to solve for these unknowns. Right. So now let me apply at point B, that is at x is equal to 0, we have y is equal to 0. So substituting the previous equation, we'll be getting C1 will be equal to m naught by p. Again, I'll go back to that one and I show. So once substituting at x is equal to 0, y is equal to 0, left side will become 0. Right side, this component x is 0 in the sense, entire component will become 0. Therefore, a cos of 0 will be getting 1. So C1 alone will be available. Whereas coming on to this case, sine of 0 will become 0. Therefore, this entire component will become 0. And the remaining thing is m naught by p. That is, we will be getting 0, which will be equal to C1 plus m naught by p. So solving this one, you will be getting C1 will be equal to minus m naught by p. That's what has been shown here. C1 is equal to minus m naught by p. Now for finding the C2 value, we can apply the second equilibrium condition, that is again at the same point at x is equal to 0, dy by dx is equal to 0. So substituting here in this case, the left side will become 0. Coming on to the right side, this one will become 0 in the sense this entire component will become 0 because sine of 0 will 0. So this component will become 0. Then going on with this component, this will become 0. So cos of 0 will become 1. Therefore, you'll be getting 0 will be equal to C2 into root over P by EA. That's it. That's what has been given here. And here, if you are equating left and right in the sense, either C2 should be equal to 0 or root over P by EA should be equal to 0. And since root over P by EA is, everything is a constant, C2 alone will be 0. So that's why C2 is equal to 0. Now, at point A, that is at x is equal to L, we know that y is equal to 0 as well as dy by dx is also equal to 0. So let me go with that x is equal to L, y is equal to 0. We'll be getting the equation as 0, which will be equal to, again, I'll go back to the same thing. Now at x is equal to L, y is equal to 0. So that is, I'm writing here at x is equal to L, y is equal to 0 in the sense, we'll get left side is 0, right side, I think already we calculated something as a 0, that is C2 is equal to 0. So in that case, the second component will not come. We have only the first component. So we'll have C1 cos at L is there, right? So cos L root over P by EA. This one will come and then plus m naught by P. We can substitute the value of C1 also, that is minus m naught by P. That also we can substitute. Right? So that's what you'll be getting for this condition. Right, that's what has been told. So C1 has been replaced with the minus m naught by P cos L into root over P by EA plus m naught by P. Right. So bringing this m naught, bringing this m naught by P on the other side, we'll be getting this equation can be written as m naught by P cos L root over P by EA, which will be equal to m naught by P. Now you can see that m naught by P can be cancelled on both the sides. So that you'll be getting m naught by P into 1 minus cos. That is, or otherwise we can take it in the other case also. That is taking m naught by P as a constant. Right. So m naught by P can be taken as a common term in the sense we will have here 1 is that minus here cos something. That is cos L into root over P by EA, which will be equal to 0. That's what has been written here. And since equating this one, m naught by P will be equal to 0. That's what we already done. So we'll get 1 minus cos L root over P by EA will be equal to 0. Or otherwise, bringing that 1 on the other side, you will get cos of L root over P by EA will be equal to 1. So when you will be getting cos theta is equal to 1, that is what is the case. So in that case, cos 0 will be getting a 0. That is the primary case. So solving this equation, L root over P by EA will be equal to 0 or 2 pi or 4 pi or 6 pi. The even cases we can write it. So taking the minimum value rather than going on with the 0, we are taking L root over P by EA will be equal to 2 pi. And squaring on both the sides, you will be getting left side L square P by EI, which will be equal to 2 square, that is 4 pi square. I need a P only, so P can be written as 4 pi square. EA can be brought on the other side, numerator, and L square will be brought to the denominator. That's what has been written. P is equal to 4 pi square EI by L square. And this is the governing equation for finding the crippling load when both the ends of the columns are fixed. Right. So to summarize this one, If both the ends are hinged, we'll have the buckling load as pi square EI by L square. So in that case, the equivalent length of the column will be equal to the unsupported length itself. If one end is fixed and the other end is free, means we derived the relationship as pi square EI by 4L square. So in that case, the equivalent length will be 2 times the unsupported length. The third case is one end is fixed and the other end is pin jointed, in the sense the relationship was found to be 2 pi square EI by L square. Right. So in that case, your effective or equivalent length will be L divided by root 2. And finally, both the ends are fixed. The Euler's buckling load has been calculated as 4 pi square EI by L square. So in that case, the equivalent length will be half of the unsupported length. So the limitations of this Euler's theory is, it is valid only for long columns, material must remain elastic, and load must be perfectly axial, and initial imperfections should be removed or ignored. So for short columns, crushing theory is used instead rather than buckling. Okay. So this Euler's theorem is valid as told only for the long columns. That is, once the slenderness ratio has to be found out, and this R, that is slenderness ratio, or otherwise which will be calculated as the radius of gyration, which will be equal to root over I by A, can also be used. If high slenderness ratio is there, means it is more prone to buckling. Yeah. So in the next lecture, we'll move on with the numerical problems related to this Euler's theory for finding the buckling load in case of columns. Thank you.